So I'd like to introduce Narang from the Harvard University. And she has just received an award from the Humboldt Foundation, supported by the Max Planck Society. So that's the reason that we are able to get her to visit us in the institute for the going week still. She received the master and PhD degree in the applied physics in California Institute of Technology. And then afterwards, she moved to Harvard University and also started her research career as a current assistant professor from Harvard University. She was formerly previously in the MIT facility. So she is an expert in the condensed matter theory and currently working in the Department of Physics. Pring has received many outstanding award and the distinctions, and just to mention a few of them, that she received the Friedrich Wilhelm Best Research Award from the Alexander von Bohr Foundation in Germany, and also the IUPEP Young Scientist Prize in the Computational Physics in 2021, and of course also the NSF Career Award in 2020, and being named as the Moore Inventor Fellow by the Gordon and Betty Moore Foundation. And also she has many also other, prize and duties, commitment in different societies. So I will not go to details. So Pring will talk about the predicting and the controlling emergent behavior in quantum matter. So please take over.
Awesome. All right. Thank you so much for having me here. I was told to keep it to an inside voice because I have a microphone on, so I'll try and not get too much into an excited state. I'm excited to talk to you though about the work we've been doing in my group in predicting and controlling emergent behavior in quantum matter. Before I start, I want to thank the talented set of students and postdocs who worked with me over the years. Many of these have gone on to start their own groups, and I'm excited for their journey ahead. Also benefited from various collaborations with people across the globe, and I noticed that a few of them are here on the call today and some here in person. I, of course, look forward to expanding this list over the next 6 months or a year that I spend in Germany. So maybe, potentially, okay. So I haven't given a talk in person in a long time, and I want to start with a story. And I'll start with the Sheldon Glashow story, so bear with me. Sheldon Glashow, if you've not heard of him, is a Nobel laureate in physics. And here's how he describes our overriding challenge in physics, okay? So he tells a story from the perspective of a visitor from another planet. He gives this visitor a name, Arthur. And he says that when he meets these Earthlings, that would be us, for the first time, Arthur is intelligent, and of course, he ends up in Washington Square in New York City. I'm a biased New Yorker, so I have to say that. And he observes two people playing chess. Okay, so it's a nice day out, and they're playing chess. And Arthur is curious. So he gives himself two tasks, and they're distinct tasks. The first task is he wants to learn the rules of the game. The second task is that he wants to become a grandmaster, okay? So all's good so far. Okay, for some reason, this is not allowing me to advance. All right, I'll just do that. So Arthur carefully watches the moves, right? So he's watching people play, and he's able to reconstruct some of the rules of the game. We just heard a gorgeous talk about being beyond the rules of the game. He learns how the pawns advance. He learns how the queens capture the knights. He gets it, right? But he realizes that knowing the rules of the game is not sufficient. Knowing the rules of the game does not yet make him a grandmaster. And in some ways, that captures how I think about physics, right? Because he adds that both kinds of endeavors are relevant. They're very important. So thinking about the technological impact, the relevance, as well as more fundamental, where we think about, what are the challenges that are facing us and how do we address them? And both of them represent an immense challenge to the human intellect. So in some ways, I'd say that over the past years, at least since when I entered science, many things had been figured out. And I think we're finally getting to the point where we're not just figuring out the rules of the game, but we are actually becoming great masters of the game. And as theorists, as people who can compute stuff, and this is why I labeled my talk predicting and controlling the behavior of emergent quantum matter, we want to think about how we can actually not just understand, but actually become choreographers of life. And I think that's where we are at. That's where theory and computation in condensed matter is at. I think we're at that transition of thinking about how we can actually control quantum matter. So why quantum matter? It's a technological pull. Joyce, in her opening statement, very nicely captured the fact that we want to think about the various technologies that are enabled by these interesting types of systems. And that could be quantum technologies, they could be classical technologies, they could be hybrids of those. In my group, we've thought about how we can actually predict things, how we can take methods from correlated electronic structure, think about new algorithms that both leverage very, very large scale classical computers, supercomputers, as well as those that can leverage small quantum devices to make predictions that would not have been possible before, ideally towards enabling new technologies. All right, so my pointer, for reasons that I find baffling, only sporadically works. So I'll try and do this using a combination of words and my hands and see how far we can get with that. So when I tell people that we predict quantum matter, in particular that we predict quantum matter across various length scales, there's this expectation that I have one acronym, one method to rule them all. And I don't. In fact, the field doesn't. There are various techniques that are synthesized from both quantum chemistry as well as those from condensed matter that allow us to think about correlated electronic structure, that allow us to think about the behavior of quantum matter. So on the left of this slide, you see techniques that and observables that you might recognize from quantum chemistry. So where you think about coupled clusters, singles, doubles, that sets the gold standard in quantum chemistry, all the way to the right, where you might be thinking about how do I look for new phases and how do I combine some of the ideas both in quantum many-body physics as well as perhaps even in ML in recognizing these phases in a complex phase diagram. In my group, we try and synthesize methods from across the spectrum in order to actually be able to predict the behavior of quantum matter, particularly behavior that emerges at length scales that you cannot easily describe by using only one of those techniques. So what exactly do I mean by that, right? There are various genres of correlations that appear in quantum matter. The simplest and perhaps also the most baffling is when you think about the electron-electron interaction. There's a lot that's been written about the strongly correlated problem. That's not the only type of interaction that we care about. So the electron-phonon interaction, as well as electron-phonon interactions beyond leading order, are incredibly important. Further, we really want to think about how we can use some of those interactions to control the behavior of quantum matter. And that involves not just going barely beyond leading order, but really thinking about some of those higher order processes. These have historically presented a challenge for theory and computation, in particular, when we think about behavior that is excited state, behavior that is the result of a drive, and perhaps where we might even include some nonlinearities by interactions with the lattice. And this is where developing new methods, thinking about new theoretical and computational methods is very fruitful. Especially, and there are people on this call who've thought about creating new states of quantum matter by driving, there is a very large spectrum of excitations that are now available to the community. So going all the way from the microwave, where you might think about coupling to superconducting circuits, to things that are all the way at an FEL facility. Most statistical and computational techniques that rely on equilibrium, that rely, say, on simplified mean field approaches, are typically insufficient to cover the behavior of such such excitations. So time-dependent density functional theory, which is typically the workhorse of people in this field, is okay, though it's not a faithful representation of all the types of correlations that can appear, as well as the types of emergent behavior in quantum matter. So there's an opportunity here not only to take existing methods and link them with stuff, but also to really develop new approaches. And the types of, so I'm gonna very quickly now transition into something that will look substantially more abstract. But when I talk about excitation, you might be thinking in a few slides, what exactly is near fields versus an external far field optical probe. So the two cartoons on the left are what you should maybe have in mind, because we will talk about where you're controlling the behavior in the near field versus where you're looking at something in the far field. Okay, so when we think about excitations that involve quantum matter, you could say, I have techniques from photonics, I have techniques from quantum optics. Why is that not sufficient for me to talk about the correlations between some external excitation, regardless of where it is in the spectral band, and that of the system I'm exciting? And the answer to that is complicated. In some cases, it works. You could take the response, you could calculate the epsilon as well as possible using a high-level theory, but that in some cases does not give you everything you want to know. And that is especially true when you're in the low photon number regime, or if you're in this regime where you're really driving the system very far out of equilibrium. Those sound like entirely different regimes, but actually they experience the same breakdown from a theory standpoint. So the low photon number regime in particular, when you think about electronic structure methods, is a challenge because most electronic structure methods treat the photon almost entirely classically. And there's been some work in how you could actually both formally and computationally merge these two, in particular when we start to think about the various types of polaritons that you could be interested in exciting. So, this advancing thing is going to drive me nuts. So that brings me to the outline of my talk. I'm not going to try and cover everything that you'd want to know about emergent quantum matter, dynamics of emergent quantum matter. I want to focus on two aspects of it that I hope will be of interest. The first, where we talk about the photon quantum matter interactions, things that emerge from that, things that allow you to create new states, as well as ones that allow you to probe and learn something about the quantum many-body physics. And the second, where we go into transport. If there are questions as I go along, please ask. I see that there is something happening on the chat, but I won't actually be able to simultaneously monitor all of these things. So our first foray into thinking about photon quantum matter interactions was in the context of saying, well, we have quasi-particles in pretty much every other sense. Right? So we think about quasi-particles in the, we can talk about an exciton, we talk about, there are other genres of things that we'll discuss here today. Maybe we can also think about photonic quasi-particles. Maybe that's exactly how I want to introduce the photon into a calculation. And we've done that to some degree. So I'd say that you could take the full response here, you have some kind of cavity, you have some interaction with the photon fields, perhaps you are in a regime of QED and you're coupling to a few level system or a many level system. Ideally, you'd want to keep all of those both real and virtual states intact. That should give you everything that you want to know about the quantum dynamics. In practice, perhaps we can replace it with this ansatz on the right here, where we essentially are replacing it with an effective vacuum where we're saying, okay, so what's different about it is that the modes of this are going to depend on whether or not I have coupling between my photon and the quantum matter here. This actually is a reasonable description, and it turns out that this allows you to capture some of the non-perturbative behavior of what happens in this coupled light matter system. And in this case, and I'm being conscious here of the fact that we're referring to matter here very, very generally, because this description in particular, you could get your electronic states, you could get your description of matter at different levels of theory, and you'd still have a faithful, non-perturbative description of what is happening in that coupled light matter system. So that's a natural question towards, well, why do I need a non-perturbative description? Why isn't perturbation theory sufficient at this point? Maybe I can go to a few higher orders in perturbation theory and then I'd be okay. it turns out again that there is a little bit of complication associated with that, is as soon as we try to compare what we get from for a very, very simple system, right? This should appear like a system where perturbation theory should maybe work. We have about 50 photon modes in the cavity, we have about 4 photonic excitations, and we have a few level system, right? So what you see here is our prediction, which is in blue here from a variational theory. So we're going from essentially no coupling, right? So this is a regime where the photon and the matter barely see each other, to a regime where the two are so strongly coupled that you should probably not try and separate them. This is a regime that would be accessible using most optical experiments. You'd probably have to be looking at superconducting circuits or cavities in this regime, which, by the way, we will as a probe of quantum matter here in a few slides. So give me a few minutes to get there. So what we realize is that our approach here is in blue. A standard perturbation theory approach here is in these dashed lines. So you realize in regimes that you have some coupling to the photon, life is good. But as soon as you really, really strongly couple to the photon, you very, very quickly start to see a breakdown of a perturbative approach there. And this is an example of where even in a simplified case where you'd expect perturbation theory to do well, it does not. So there's an argument to be made for actually invoking things that are simultaneously taking the many-body dynamics into account. There's not very much many-body dynamics here on the matter side at the moment, as well as the non-perturbative behavior of the photon simultaneously. And there are observables that would emerge from that intersection that would be different than what you would get from a conventional photonics calculation. All right, let's just take a simple case, right? So we'll start out simple. We'll go from interaction to the lattice. We'll have the lattice and a magnon, and then we'll get to other collective modes that will get increasingly complex over the next few minutes. So the simplest case is I have a polar material. This could be hexagonal boron nitride, silicon carbide, your favorite perovskite. As long as I have some phonon to couple to that also interacts with light, I can talk about the response of this in terms of that polaritonic mode that I can excite, right? And this is something that looks very similar to what you would see from other kinds of collective modes that are excited that live on a surface. This could be similar to a plasma polariton. This could be, there's a whole zoo of these out there. What's key here is that we have something that's polar, it's talking to light, and I can talk about this splitting relative to the light line. Right, so the light line, or actually technically the cone here, is what separates out the two polaritonic branches. Okay, so the promise of doing everything by interacting with the lattice is as follows, right? I still get that same extreme confinement. I can get very, very, very strong interaction with light, and yet I'm out in the mid-IR where maybe things are harder to do other ways, as well as it's a regime where I can actually not be as susceptible to loss as most conventional dielectrics or even plasmonic systems are. Okay, so that's all well and good. We started on this path of thinking about how you could describe such an interaction for a simple system, a known system like hexagonal boron nitride, and then how you could use this to predict other systems where you'd have similar phonon polaritons. So I'm giving you the next a couple of minutes here, so you have a preview of what's going to happen. I'm going to tell you about phonon polaritons in a simple system. I'm going to tell you how we predict them for an oxide perovskite. These are yet to be realized in monolayer oxide perovskites, and how you can use these phonon polaritons now to actually change the coupling of something else to that oxide perovskite. So it would be both a way of coupling as well as something that would be a way of probing that interfacial interaction. Okay, so that's a long-winded way of saying that there are going to be a few equations now. So please, I hope I won't lose you. So we can think about such phonon polaritons in true 2D as essentially being in terms of the conductivity of this polar monolayer. And now we, of course, need a few different things, right? So knowing something about the phonons would be useful as I'm talking about interactions with the lattice. I'd also want to know something associated with the dissipation. So at what point would this start damping? And these are things that we can get microscopically. You could also equivalently, figure these out from your favorite enzyme measurement if you wanted. We take along a wavelength limit, and we actually come up with a fairly universal parameterization of the conductivity of a polar monolayer. So I call it universal in particular because, you know, it's not just something that's going to work for a system that we know about, like hexagon-boron nitride, but it's also going to work for something that we haven't yet seen or has not yet been measured. So everything works pretty well for hexagon-boron nitride, even though you'd say that it still has mysteries. You'd say, yeah, okay, hexagon-boron nitride, I know I can make a monolayer. I can distinguish a monolayer from a few layers of hexagon-boron nitride. And as we expect, we see very, very good agreement between what we predict for a polar monolayer of hexagon-boron nitride with what you can get from an ensemble measurement. Following this, and this is not something I'll have a chance to mention here, but I'll give you kind of an idea. These phonon polartons for hexagon-boron nitride can also be reporters of what's happening when you have a stack of things that are coupled to this hexagon-boron nitride. So it's very fashionable now to talk about things that are twisted and then encapsulated with the HBN. There's a lot that has been said, written, and also perhaps some things that have not yet been said about it. What we realize is that this very simple idea of using phonon polartons can be a very good probe of that physics. So, okay, so that was hexagon-boron nitride. So you'd say, well, is there something that you can look at that has not yet been observed using this polar this formalism for a polar monolayer that you just showed? And so we were actually thinking about these oxide perovskites and said, well, can you actually have similar phonon polartons in, say, a monolayer of strontium titanate? Strontium titanate is the fruit fly of people in condensed matter. Lots of amazing things happen in strontium titanate. And it just turns out that in 2019, a true monolayer of this material was synthesized. So a few other things that are exciting about this idea of using phonon polartons as a probe with strontium titanate is that you could think about the stacks that people have made with STO, iron selenide and STO, and you could use what's happening in the STO, the phonon polarton, as a probe of that coupling. Perhaps you could use that to turn on and off that coupling. Perhaps you could do other things with it. So the simplest thing that we could do was say, okay, let's just put it into that formalism that we have and see if the whole thing actually works, right? What does the dispersion look like? Does the dispersion do anything that is even remotely close to hexagon-boron nitride? Does it matter? And all of those things actually were quite interesting. So we got bold and said, yes, STO has been synthesized as a true monolayer, but perhaps you could also look at, true monolayers of lithium niobate and of other types of similar ABO3 perovskites. Now, there are a couple of things that are different between HBN and these oxide perovskites. And it's maybe evident from this that HBN, everything pretty much lives in plane. However, with these oxides, you start to see, of course, things that are out of plane, and that starts to look worrisome because you'd say, I've described everything in terms of the conductivity of this layer, and maybe I'm not capturing all of the behavior out of plane. So we've been able to incorporate all of that. We've been able to think about what you could do if you were, say squeezing this phonon polarton, or in other ways engineering various interfaces that use this coupling to, say, STO, and maybe if you wanted to do some nonlinear optics, you could also think about what happens with the lithium niobate monolayers. So this was the simplest case that we could construct with having a coupling to the phonon polarton and using that as a probe of something that might happen that is related to mysteries in superconductivity. So we got even bolder and said, well, how about we talk about controlling some of the behavior? And now this is where the situation gets a little more complicated. So we're going to look at a cuprate parent compound, YBCO. Don't worry, it's not all that relevant right now that we're looking at YBCO. We're going to think about some kind of resonator that's going to allow us to couple to this. This could be a near field coupling, and in a second you'll realize why near field coupling with the tip is in fact a good idea here in this case. And of course, in such a situation, we're going to try and couple to the antiferromagnetic fluctuations in this parent compound. Okay, and those fluctuations are in fact believed to be the pairing glue for the Cooper pairs in the superconducting phase. And we're going to try and control them via essentially coupling to an infrared active phonon in the system, right? So in the previous case, all we were doing was coupling to the infrared active phonon mode. We were just talking about how you could actually use that to create a collective excitation. Now we're going to add this complexity where we're going to say that phonon mode maybe can talk to this resonator, and maybe a combination of talking to the resonator as well as talking to the magnons will allow me to change something associated with this very well-known cuprate parent compound. Okay, so what exactly is happening microscopically? Microscopically, we're thinking about the spin wave excitations of these nail-ordered spins, and we're talking about their interaction with the phonon mode. Okay, so at that level, this is a linear order coupling. You would require spin orbit coupling in order for this thing to not essentially vanish, but it has a couple of things that are complex, right? And the first is that I need some very awesome resonator, and it's got to pump in a lot of energy into this system. And that's a little bit challenging. By the way, if you're interested, this is work that is done by a combination of John Curtis and Nick Poniatowski. They will both be hopefully joining me for some part of this visit here in Germany. Okay, so everything is well and good so far. Energetically, to linear order, this makes sense. We can do this, by the way, both for a single layer and bilayer YBCO. I'm not going to look at the more complex case of twisted YBCO. There have been recent reports of twisted layers of YBCO and interesting stuff that happens there. Let's disregard that for now. So what we realize immediately is that if we're just exciting the magnopolariton and using that and thinking about squeezing that, that's limiting because I need to actually pump in a lot of energy. So maybe I can go to the next order and I can think about coupling to say the bimagnon operator in this case. And that turns out to actually be quite fruitful. So this is a higher order coupling. So it's only present in bilayer systems. And in fact, if you were kind of looking at the symmetry of the previous case, you'd say, yeah, there's inversion symmetry. So why did you stick to linear order? You would be right. I assumed something about the finite momentum near field coupling that would allow me to actually, get this whole thing to go. However, when I go to this bimagnon case, I realized that interaction can actually be very strong in part because there is a nice Van Hove singularity that allows me to do something interesting there. And there are a few things you notice now by looking at essentially the electromagnetic absorption. This is the magnon contribution to it. Okay, so this is not everything that could possibly happen. And we're looking at 3 cases where essentially our ordering is along the A-axis. So our spins are aligned. We're looking at a case where there's a 45-degree and then a 75-degree angle there. What you see is that actually there are changes to the dispersion, quite significant changes to the dispersion. So there is a way here that we could control the phonon, we could couple via the phonon to the magnon, use that both to essentially cause a way of squeezing as well as a way of actually controlling the superconducting order parameter here in a way that is parallel to all the other techniques that have been used. We show this for YBCO. Why? Because it was a nice, hopefully well agreed upon system. But this is something that could be extended to other cases where you can have both magnons and bimagnon coupling. So I'd say that actually wherever you have terahertz excitable magnons, this could be a general way of controlling the order parameter there. So we've done 2 things so far. We've simple case, we have phonon polaritons, and the other case where we've used it to control. Now let's think about other more exciting collective modes. And this is now getting to be in the order of controversy in some ways. So we're going to think about collective modes that allow us maybe to say something about superconductors where not much is known about or not much is agreed upon. And those 2 can be in some ways the same thing. All right, so when we think about a superconductor, and you can, your favorite copy of Tinkham or whichever text that you refer to, we typically think of it as something at the mean field level. However, there are very interesting dynamics of the order parameter that show up, and in fact, the collective modes, which is what that essentially refers to, are also important. So the one that has been in the news quite a lot recently is the Higgs mode associated with this. And so you could think about the phase and amplitude associated with a certain order parameter. You would get your nice Mexican hat potential. We and others have done this with various types of order parameters for some time, right? So this Higgs mode in particular should in some ways be a very good signature of what kind of superconductor you have, because you could say, well, it's essentially mapping directly to the symmetry of my superconductor, so I should be immediately able to say something about it. Okay, so there's a little bit of challenge associated with that, but what we wanted to think about is maybe some of the anisotropies associated with the various collective modes, and this is not the only kind of mode you could excite. Maybe there is something that we could say about unconventional superconductors using such collective mode spectroscopy. The other thing that, by the way, makes this collective mode spectroscopy exciting is that they're both from an optic standpoint as well as from an yield standpoint, some advances that allow you to talk about these modes. Okay, so these modes, and you could look at some old literature, people have talked about in principle these should exist, but in practice they have been notoriously hard to find and to be able to identify, right? So, but I could say something associated with, say, the nodal symmetry here associated with the modes. Maybe I could even say something interesting about existing and well understood superconductors. All right. So what we wanted to do is take these ideas and generalize them to unconventional superconductors to know something about these multi-component order parameters that would not be easy to get from other techniques. All right, so in particular, when we're talking about time reversal symmetry breaking, we have a multi-component order parameter. And in fact, it's not just multi-component, but there's actually a relative phase and amplitude associated with that. And that is exactly what we're going to try and identify here in terms of the collective modes that we get. So there's been an explosion of materials, and there is a conjecture out there that, in fact, maybe many of these systems are all time reversal symmetry breaking. We just haven't been looking through the right lens at them, right? And there are various reasons to look for time reversal symmetry breaking superconductors from a technological standpoint. I'm interested in them because, well, they're fun and controversial. So within the last few years, Strachan-Brusnade has made a renaissance. It's been around, and then there's been controversy, and it's back. It's in and out of the news. It's quite interesting, right? Then there are these heavier compounds that are based on uranium. Uranium telluride in particular has really captured the attention of many people. The Moiré heterostructures, I think everyone and their grandma is talking about the various ways that you could use Moiré heterostructures. And of course, there are interfacial systems where you could break time reversal symmetry in other ways. So what would be useful is if we could say something quantitative about these, perhaps an experimental prediction that could be actually realized using current techniques. Okay, so the way to think about the collective modes here would be that we want to think about the internal structure of this multi-component order parameter. I want to figure out what that relative amplitude and phase concept here would be, and I want to say something about these modes, right? So you might recognize some of these modes as being clapping modes from the helium-3 literature. They're clapping modes and they're flapping modes. Whoever named these really needed, a better PR team. But anyways, what is not obvious a priori is that these are well-defined modes, right? Because we need a couple of things. We need to be below the quasi-particle gap. And we also need to, of course, not be not have things that are scattering into various nodal channels. And that's something that actually requires us to know something microscopically. And this is where just looking at the symmetry, just looking at what the order parameter is doing itself is not sufficient. This actually requires some of the microscopic calculations that I was telling you about earlier. So our warm-up case is the canonical P plus IP case. And so now you're looking at the spectral functions for, this is perhaps the most famous one and pairing in 2D. What you see, okay, so I should be precise about this. Now I have an angle eta here, right? And that refers to the mixing between the two. What you immediately see is that for an equal mixture, right, of this, you have well-defined modes. In fact, we realized that these there are some general statements you could make about this that would be, I think, quite interesting for people who are looking at clapping modes in P plus IP systems. Now, that's okay, and that's maybe a system where you'd be able to find some literature. You could also say that you could look at more exciting combinations. You could look at D plus IG, you could look at D plus ID prime, or you could look at S plus ID. And there are various schools of thought that say, this is something that represents what's happening in the nuclides, what's happening in some of these Murray heterostructures. And without going into the gory details of which one should correspond to what, I want you to walk away with the fact that there is, in fact, a way of using these collective modes. These are those very same emergent excitations that I talked about earlier in my talk that could allow you to say something quantitative about time reversal symmetry broken superconductors. In fact, there is a pathway to experimentally detecting these. So for the relative phase mode, I'd say that some of the yields techniques would allow you to get the AC compressibility. That should be, I think, quite good. There are also, of course, microwave absorption and other types of terahertz techniques. Of course, when you talk about the amplitude mode, you want to think about something that is in the nonlinear terahertz. So there's a lot to do here. I haven't cited the, we have a paper out on this. I apologize if I forgot to include the citation here, but I encourage you to go look at it and share your thoughts on it. Okay, so I'm going to transition now from talking about the excitations that we've been kind of going over this complexity ladder and switch gears to talking about transport. And I see some folks in the audience who, at least the physical audience that's present here, that are interested in transport, and tell you about some of the mesoscale physics that appears here. In particular, how we would take some of the microscopic properties that we've spent a lot of time calculating and take them to a length scale that is hard for theory. So how do I take things associated with electron-electron, electron-phonon, phonon-phonon case, and say something quantitative from a transport theory standpoint, okay? So we've been in this business for some time. In fact, we've looked at both spatially resolved electron transport as well as spatially resolved phonon transport in the past. In terms of spatially resolved electron transport, okay, why spatial resolution, right? So when we have things like interfaces, I have things like nanostructures, I have stuff happening, right? There's a spatial component to it. And usually I can take things and say something about the overall transport if I ignore the spatial degrees of freedom. But that's not necessarily a good assumption. What we've developed is a technique that uses large GPU systems. It's something that is inherently GPU based that allows you both to discretize these complicated nanostructures, these interfaces, and then allows you to then keep all of the microscopic information you've calculated from first principles and take it into a transport framework. So a couple of things you could do with this. You could ask questions like, I have electrons that I'm somehow injecting into the system here. They're going through 4 or 5 interfaces. What's happening here? I could do that equivalently with phonons, including things like phonon scattering and reflection at interfaces. Or I could ask in a nanostructure, how are things thermalizing if I've excited them and perhaps I'm generating some hotspots of certain sort. Okay, so in that case, you'd also maybe at long times, so initially, of course, in the first few picoseconds, thinking about temperature is maybe not a good quantity, but many of these measurements are made well beyond that time range. And at that point, you could talk about, temperature-dependent material properties. So this is explicitly and inherently included in the types of calculations we do. Am I doing okay on time, by the way? Am I doing okay on time? Okay, awesome. All right. So we're thinking about this type of transport. And by the way, this is work by one of my first students who graduating, Georgios Varnavides. And this is a technique we've introduced that allows you to think about spatially resolved transport at very large scales. It includes essentially all of the interesting phonon dynamics that you want to have. So it's titled Spatially Resolved Transport of Non-Equilibrium Species. It's species in particular because you could do this for electrons, you could do it for phonons, and if you somehow magically had the scattering matrices associated with many magnon interactions, that could also go into this. We wanted to go beyond the relaxation time approximation, so actually we can get things that are truly non-equilibrium, and this is part of the reason why we introduced this method. Now, there is a rich literature of transport formalisms, and these have been around for a while. So our equation of interest, right? So we of course, and by the way, the one term that has brought a lot of attention recently is this tunneling term, at least when people are talking about these Wigner transport methods. That's perhaps the one that at least relating to the talk that Titus gave right before me. But there has been for a while, a set of approximations people have had to make. And the biggest one, of course, has been to drop anything associated with the spatial component. Okay, so we don't make that approximation. In fact, we have explicitly, of course, the rate of change, the drift, the source term, and the collision matrix elements that we would get from ab initio calculations. So that is included here, and we have a fully non-equilibrium carrier distribution. Okay, so that means that we're keeping, things like, okay, there was something that was generated here. Perhaps if you're doing this in a fancy STM context, this is a good way to go. This is a nonlinear 7-dimensional integral differential equation and is explicitly, something that we can compute. So we can take a steady state limit if you want to assume that things are being measured in a CW context. We can linearize. We can get something that is this scattering matrix, which gives us the rate at which things are going from one of our well-defined states to another. Well-defined state here is important. The fact that it's a real state or virtual state is not important because both of those are actually incorporated. So if you have something that is mediated by a virtual state, for example, if you have a virtual phonon-mediated electron-electron interaction, that actually is totally fine here, as long as where you eventually end up is a state that exists. Okay? Okay, so all of this is how we implement it. I see that there isn't that much interest in this aspect, but for my computational physics colleagues, I think you'll recognize that this is something that is challenging to implement. All right, so the final component that we include here is the interfaces, and that includes things like interfaces where there's a lot of strain, perhaps the interfaces where you might actually start to see phonon reflection, and we have shown that. Okay. So all of that to look at a concrete example of where some of these transport signatures show up in particular, and we heard a beautiful talk about vial semimetals right before me, so I won't tell you what vial semimetals are or what is interesting about them from a topological standpoint. I will say that they have some very interesting transport behaviors as well. And there has been a lot of debate around electron flow in some of these vial semimetals, asking if the behavior of these systems in transport is driven by the topology, or is it purely a coincidence that some of these have interesting unconventional transport signatures, right? So if I tell you something is unconventional, I should tell you why and how you think about conventional transport. So in typical conductors, you'd see something that is pretty much diffusive. Things would scatter off of impurities, vibrations, things that our electrons are encountering. This is very similar to something that would be a momentum relaxing process, right? So pinball machine is the visual I have. The presence of strong electron-electron interactions, you'd say that some of these other scattering pathways become less relevant, and I start to see momentum conserving interactions. So what you need for there to be a collective flow of some sort, ideally something that looks like a spatial behavior that doesn't show up in typical conductors, you need these electron-electron interactions to be pretty strong. There'd be two questions around that. First, how strong are these interactions and to what temperatures do they persist? And the other, what is actually mediating these strong electron-electron interactions? So both of those questions are important. And in fact, measuring such spatially resolved transport signatures is also incredibly hard. So the technique that I'm partial to is this NV scanning magnetometry. It's something that can tell you exactly what's happening in, say a monolayer of some material. So you could actually map out exactly what the current profiles look like. You can back it out. Well, you're measuring the fields, and then you're backing out what the current profile looks like. You can also think of something like a scanning CNT transistor, as well as squid microscopy. And there's a lot of work happening in both of those areas as well. So collective flow would imply that there is some phase front I can talk about, right? So there's something that looks different from this pinball machine, where I can't actually distinguish whether we're going from point A to point B as a team, or if we're just ending up there in a diffusive manner. In order to see a phase front, maybe we should talk about a set of length scales that go with it. And the length scale of interest here would be something that is either the channel, something that you can actually pattern, and how it competes with the other two length scales of interest, right? The momentum conserving and the momentum relaxing processes. So this is a tale of length scales where we can talk about 4 extreme regimes, right? So there's the Gurji, where we can essentially see this very nice parabolic flow. This is a paper from the 60s from, Professor Gurji. There is the Knudsen regime, which kind of looks a little bit boring. It's more of a flat top. And then, of course, the porous and the diffusive, right? So diffusive is the one that you would expect to see in a typical conductor if all is kept the same. So the extremes are not what's relevant. In some ways, there's a whole spectrum, and this is where we've actually introduced some ways of thinking about it, perhaps even a new lens that allows you to say, I have our momentum conserving, momentum relaxing interaction, I have a geometry. Can I think about the curvature of the current density, or I can think about the conductivity? Would this tell me which regime I'm in relative to those 4 extremes? So I'm looking for something that looks like this nice parabolic flow. Maybe I can, if I get ambitious, even call it hydrodynamic, though I recognize that that word itself is a little bit of a hot button issue. And so what you realize is that, you want to have the momentum conserving interactions far exceed the momentum relaxing, but you also want there to be a good correlation with the geometry, the channel width that you're going with. Our prototypical system for this was tungsten itelluride. It's an exciting bald semi-metal. A lot of people are talking about tungsten itelluride. And this is a system where there's some debate whether the electron-electron interactions are coming from the standard Coulomb-mediated electron-electron interaction, or if, as we say, it's something that could be even phonon-mediated. Right? So remember, for that collective flow, all I said you need is strong electron-electron interactions. I never said that it needs to be Coulomb-mediated. In fact, I'm going to argue here that the phonon-mediated electron-electron interaction in this case, in the temperature range where people see collective flow, actually is the dominant physics. It interestingly is the same diagram that also shows up in the conventional theory of superconductivity and something that might relate to other phases in tungsten itelluride. But we realize that, and I know I'm going to quickly run out of time here, but let me just tell you. So this collective flow doesn't persist across all temperatures, right? Obviously, at very low temperatures, I'm going to see different physics. My sweet spot will be something around the 20 to 25 Kelvin regime, where I start to see a crossover between the momentum relaxing and the momentum conserving processes that become the dominant physics. And we see signatures of unconventional transport, of non-diffusive flow in this system. And this is where you could almost play a game here. Could you identify the prediction versus the experiment here? So the top here is what was experimentally measured. Bottom is the prediction. There is no free parameter here. We see is very, very, very clear evidence of non-diffusive transport in tungsten itelluride. And this is exciting to us because this temperature dependence is in fact what allowed us to say, there's an area where you see peak unconventional transport, and there are other areas where perhaps it smears out. The the spatially resolved transport method actually captures this non-monotonicity. We see a peak around 15 to 20 Kelvin. I'm sorry, I said 25 earlier. And this is not something that can be explained by the standard Coulomb interaction. This is something that requires the phonon-mediated diagram that we've been able to calculate, and something that this is an example of a violet semimetal where we've seen this. There are other violet semimetals where we have also predicted and identified such behavior, including the PRX that I'm citing there, where the same phonon-mediated diagram actually is responsible for very unconventional transport signatures. Okay, so I want to spend maybe a couple of seconds saying that I was going to talk about some of the behavior of Fermi surfaces here, in part in anticipation of Tito's talking before me, who would show Fermi surfaces, but he did not. So now I'm going to have to tell you that the Fermi surfaces of some of these violet semimetals can be quite kooky looking. Okay, and if you make an assumption that the Fermi surface of these is nice and spherical, which by the way is the dominant assumption in all transport methods, we will go out there and say, I have a cool transport method, and then take a very very simple approximation here. But if you look at some of the ARPAS measured Fermi surfaces, perhaps like those from Niels, you'd realize that there is a lot more complexity. And this in fact shows up in terms of easy and hard directions for the type of transport that I just talked about. A really good system for this is palladium cobalt oxide. There's been a lot of discussion and debate around that system, where you can look at what the Fermi surface is doing to the transport. So the fact that there is a preference for direction. So now at this point, I'll just say that this is a system with palladium cobalt oxide in particular, where there's been a lot of discussion recently. And the fact that we can incorporate the exact Fermi surface of the system into our spatially resolved transport method actually has allowed us to resolve some of this debates, to say, where is it that it's purely ballistic, or where is it that there are some signatures of unconventional transport showing up in this type of system. So again, this is looking at very pretty much the same LMR over the geometry, LMC over the geometry. What you realize is in one case, I have the surface that is aligned with the direction of transport, and another where it's rotated by about 30 degrees. And you see that there is a very strong transport anisotropy that emerges from just that very, very simple case. And in many ways, looking at palladium cobalt oxide, this is a prototypical case. This is perhaps the simplest Fermi surface that we could get that isn't spherical. There are, of course, many others where you'd start to see the behavior really strongly deviate from what you expect. Okay. The take home from this is that, when we think about transport in these violet semimetals, the role of phonons is in some ways underappreciated. It's something that could be, I think, much, much better understood, and would actually give us a good understanding of what's happening in this system. So let me just see if I can bring my cursor back here. I lost my cursor there. All right, so in the last maybe couple of minutes, I just want to tell you about some of the ideas we've been thinking about for the future. So there are two different regimes I told you about with the emergent behavior in these quantum materials. One was where there are collective excitations, another where there was something associated with transport. What we want to do is find a way to probe the behavior of those two beyond transport, while leveraging those collective excitations to learn something about types of quantum matter that either have yet to be synthesized, or ones that have been synthesized but very little is known. What we've been doing in this space is actually taking a slightly different view on this and probing it with these superconducting cavities. So now you can think of these superconducting cavities as essentially being circuits that you could describe using an LC circuit. Your favorite EE course would have maybe gone over it, and I could think about essentially placing my magical quantum matter somewhere in the middle of this circuit. Okay, this would be the dream. The dream would be that something happens either with the quantum capacitance or the quantum inductance that's different. Something shows up in the signatures that tells me beep, 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 I'm a fancy quantum material, something interesting is happening, and here's exactly what it is. Okay, so that's at least the dream. And the other reason why we think this is not such a a crazy idea is because, you know, these cavities are very, very sensitive. In fact, they're used to do various kinds of noise spectroscopy. There's very high Q, so they're very sensitive to environments. If something is going to pick up a change in what's happening, it should be these cavities. As long as I can align in some ways the energy where all the action is happening. So these are things that would be in the gigahertz. Maybe you could, with some other things, push them out to the terahertz or down to the megahertz. But it just depends on the type of resonator and whether you have a single resonator or array of resonators. Okay, so and the reason this could be bringing it a full circle back to the types of unconventional semiconductors that we did some of the collective mode spectroscopy on, you could say that the many body density of states would be something that manifests in the quantum capacitance. You could also think about the superfluid density that shows up in the context of the quantum inductance here. These have, of course, been thought about, but you could also now think about constructing resonators that are not just a single resonator, but perhaps even cross resonators that are essentially an equivalent of the kind of carrier rotation measurement you would do in, say, a conventional optics setup. And that could be a very, very direct probe of unconventional pairing mechanisms. And if we get even more complicated, you know, you could have, say, a system where you establish what's happening, you deposit something on top. Now you know what the changes are that are introduced by this interfacial coupling. You essentially have a modular platform for knowing exactly what type of behavior is showing up in cavities. For me, this is a fun intersection between, you know, cavity design and photonics as well as condensed matter. So with that, let me summarize. I told you a little bit about dynamics and emergent quantum matter. We started with simple cases. We got a little more complicated. And then we talked about transport, especially some of the mysteries in unconventional transport. And we brought the cavity back a full circle in saying how we actually can understand the behavior, how we can probe the behavior and design new systems that way. So I want to acknowledge funding for my lab from various folks. I'm particularly grateful to the Gordon and Betty Moore Foundation for supporting me in essentially being able to do all of this work without too many questions asked. And I want to, of course, thank my group again. Thank you for your attention. Happy to take questions.
So yes, thank you, Prin. Very interesting talk. So now we look forward to the questions. Yeah, Roddy? Okay.
Thank you very much, Prineha, for the amazing talk. I have a question on these clapping modes, the Higgs mode. If you could go to that slide.
Head back there. Give me
maybe
second.
You don't even have to go back to the slide. I just asked my question. So that discussion of the Higgs modes in the superconductors has been ongoing for many decades. And usually people were assuming that the Higgs mode should be generically overdamped, and it's very hard to resolve it experimentally. So might this not also create an additional bottleneck for employing the great ideas you have communicated there, and more an add-on? What, in addition to the parity of the superconducting order, are you expecting to learn from the Higgs mode? Because it just lives in the irreducible remainder representation of the gauge field that preserves as symmetry takes in. So it's U1 to Z2. So I assume the Higgs mode will only be able to distinguish even and odd parity. What beyond that can you resolve?
Yeah, so I want to be, so thank you. That's an excellent question. And I want to state that, you know, when I talked about this, it was going beyond the Higgs mode. I recognize that even getting the Higgs mode itself is hard, but actually these are generalized versions of those clapping modes. And in fact, these are, as long as you're below the gap and you're not scattering into one of the nodal channels, you are in fact very sensitive to the relative phase in that multi-component. What we established quite I think concretely is that these modes, we know they should in principle exist, but from the microscopic theory, we know that they're well defined, and they are actually distinguishable. So this is not something that is, I didn't want to go into details of Matsubara sums here today, but I'm happy to go over that with you in detail. And that was important because it's, you know, it's not just from a symmetry standpoint that we're saying that these modes can exist, should exist, but actually, you know, how you would explicitly distinguish them. So, and I think, if I may, there would be signatures that I think EELs or other terahertz spectroscopy measurement should be able to resolve. Yeah.
Okay. So next question, Titus.
Yeah, thank you very much for this great talk. But I have a question about the non-diffusive transport part. So the hydrodynamic,
Yep.
the hot button transport. Is it? Can you say something about what the ingredients physically are that will give you this type of transport? Based on your numerics, because I guess with the wire semi-metals, there's sometimes this kind of question: is it really the wire node or not? There's like, I'm more familiar with the magnetotransport, but sometimes there are materials which look exactly like a wire semi-metal. We know there's no wire node, and still there's the same transport. So can you say something about like what's the physical mechanism to give you this information?
I'll answer those two questions in series. I'd say what is the role of the node and where the node is relative to the Fermi level, and actually how much it's contributing to the transport is very much debated. What is not debated is that you need these strong electron-phonon interactions. In fact, I take that a step further to say this phonon-mediated electron-electron behavior is actually what's giving some of this unconventional transport. Now, could those same diagrams dominate in other systems? We don't know yet. I'd love to figure out how we can collaborate to do this larger search through some of these other kinds of materials that have already been predicted. It's a complex diagram to be able to predict, but I'd say that it'd be worthwhile if we could identify beyond some of the prototypical systems that exist as to what is going to show this unconventional transport. I don't think that the nodes, are directly, I can't point to, hey, if I got rid of the nodes, this signature would go away. So that direct line doesn't exist. However, I'd say it would be an awful coincidence if this is showing up in type 2 vowel semi-metals so extensively and not in other systems, and that you couldn't draw some conclusion about the topology from that.
Okay.
I have a very basic question because I'm out of the field, but a lot of the description with the dispersion relation, strong coupling and so on, I feel is really in a very static picture. I mean, the whole concept of modes come from, you have to solve for eigenstates and so in a very steady state kind of picture. Yet, then you talked about transport and try to introduce the time dependence, but then d by dt is gone after in the transport. So I'm wondering, what do you think would be the approach to study transients? I mean, do these results hold if one really wants to study at maybe femtosecond or attosecond scales? And if they work, then why when everything is so static?
Okay, so thank you. That's an excellent question. I'd say if you were thinking about attosecond or even femtosecond physics, you're talking about the modes statically is not a great approximation. I think.
I'm going to build it up, so
right.
Whether or not it works, I think it depends on the build-up time of the mode, and if you have very high cavities, it
right.
will take maybe nanoseconds.
Exactly. So I think in the superconducting cavities, this is like a good approximation where you can separate those two timescales out. I think looking at these terahertz resonators where maybe you couple in both the drive as well as the strong coupling, I think that would be something that, current techniques, including ours, would not immediately be able to capture. And the inherent assumption, at least from the standpoint that I showed here today, is that there's something happening in the matter where that excitation and the cavity are hybridizing in a way that is different from all the other decay and time dynamics going on. And so that was, a fundamental assumption that's been made. Which is, at least in the Magnon case also true, right? Because those modes are not going to live forever. So so I'm assuming that there is enough time for both the hybridization and the control to happen before you start to see a decay of those modes. This is not something I'd be able to say, for example, with plasma polaritons. Yeah.
Okay, so I think we go to Stut. So no, then no question. But if anybody have question, you can put on the chat still.
Well, thank you very much for the very nice talk. I had a question coupling your discussion about monolayer oxides, in particular STO, and of course you've discussed superconductivity. And I wondered, of course, as you know, interfacial superconductivity in some of these oxides, you also mentioned potassium tantalate, is super exciting. And I wondered if you had any comments about the mechanism, or can you make predictions about which types of interfaces or monolayer oxides might be superconducting?
Excellent. And I'm glad we're concluding on that question. So some of these monolayer oxides, people have shown in monolayers of iron selenide coupled to these oxides, where you see a change in TC of the iron selenide in that case. I think that with maybe not STO, but some of the other AbO3 oxides, there would be an opportunity to also see a change in the STO or in the oxide itself, but probably not with something like iron selenide. So there are various chalcogenide oxide combinations that have been looked at. I think they've almost all exclusively focused on the monolayer being the chalcogenide and the substrate being the oxide. I think if you inverted that, you'd probably also see very interesting and perhaps different effects, as long as it's electron phonon mediated. So this is the premise in all of the interfacial work that we've seen so far, is that there is some coupling happening at the interface that is mediated either by the very special phonon mode or some other electron phonon process. So I think if that's the case, then with these monolayer oxides, even the simple ones coupling to a boring chalcogenide, you'd start to see some very interesting effects.
So maybe just follow up. So the iron selenide you mentioned, so that is superconducting maybe at 100 degrees Kelvin. So is that something you can predict?
We can try.
Cannot predict. Okay, thanks.
Okay, so I think the time is flying. I don't know if there's a question. No, there's no. There's a question to. This one. Okay. So can you please comment on the effect of the temperature on the phonon polyritotic modes? Also, please comment on the order of the magnetic field strengths required for realizing Magellan polaritons in YBCO.
Right. Okay. So the impact of temperature for the phonon polaritons is actually incorporated in both the fact that, when I showed that expression, I said we have the dispersion as well as the damping there included. So that's incorporated. I think, of course, being and doing low temperature SNOM would be great, but these are effects that also show up pretty much at room temperature. So this is not just low temperature physics is the point. I know with a lot of the work in polaritonics, that's a question that comes up. Regarding the field strengths that are required, let me get back to you with an exact number. I don't have that offhand. I do want to explicitly state that we are making assumptions about how much you can couple in via that set of resonators that would sit with the YBCO. So maybe YBCO is not where this is realized, but some other parent cupric compound. Yeah, but excellent question. And whoever asked me that, please feel free to email me.
I hope that you are happy with the answer.